welcome back. Today is the day 5 of week 4. So in the last class we learnt about the theorem called the Great Orthogonality Theorem, and we also learnt about 5 important rules that come out as consequence of that Great Orthogonality Theorem. So the rules were the first rule were the sum of dimension square is equals to the order of the group, and second we found that sum of the characters square for any given irreducible representation is also equals to the order of the group. Okay. So also we learnt that any two irreducible representations are orthogonal. This is equals to 0, and we also learnt another two rules, fourth and fifth, which says that the number of irreducible representations equals to the number of class present in the point group. Okay. So the fifth rule is that the characters corresponding to the symmetry operations belonging to the same class are identical. Okay. So the characters for any given R, so if there are 1, 2, 3, 4 different number of symmetry operations belonging to one particular class, then they all will be identical. So after getting these 5 rules, we took an example of the point group C2V to illustrate these 5 rules. So what we got in that case is the character table. So using those 5 rules, we could form the character table for the point group C2V, and this character table contained all the irreducible representations that are possible for the point group C2V. Now one thing we should notice here that we also mentioned during introducing the character table. I will reiterate again here. So now you see in this character table there is one particular irreducible representation which has all of its characters as positive 1. Okay. So what does that mean? That the characters of this irreducible representation are symmetric with respect to all the symmetry operations of the group, correct? Because plus 1 means it is symmetric, the character is symmetric with respect to that particular representation. So you will find that all the character tables for all the point groups, one irreducible representation will be such that characters of all corresponding to all the symmetry operations are plus 1, and this particular irreducible representation is called totally symmetric irreducible representation. Okay. So for any given character table, if you have to form, then you know for sure that one totally symmetric IR will be there. So this knowledge will even help you even more when you would like to form the character table. So as a second illustrative example where we can show that we can form the character table utilizing those 5 rules which are consequences of the Great Orthogonality Theorem, and we will take the example of the point group C3V in this case. So a molecule which has a point group of C3V is like ammonia, right? Now we will try to form the character table of C3V. Okay. So what are the symmetry operations that a point group C3V has? So C3V has identity, it has C3 as the principal axis of symmetry. So, therefore, the operations generated from that will be C3 and C3 square, and there are 3 sigma v's. So, sigma v prime and sigma v double prime, and these sigma v's are along the NH bonds. Okay, if I take ammonia as the example for C3V. Now, we also know that C3 and C3 square, they form a class, and sigma v's, all 3 sigma v's, they form a class. So, our rule says that like what is written for rule 5 here on this board, it says that character corresponding to sigma v prime and sigma v double prime are same. Similarly, characters of C3, C3 square will be same, because this forms the class. So, therefore, while writing the character table, I do not have to write explicitly C3, C3 square, sigma v prime, sigma v double prime. Instead, what I can write is this, like instead I can write 2 C3, because C3, C3 square will have the same character. So, without repeating all these characters, we can club them together. So, similarly, I will have 3 sigma v's, and now with this we have to form the character table of C3. So, what we learned in the last class is that first we have to determine how many irreducible representations are possible. Okay, so the number of irreducible representation is equal to the number of class. So, we have total 3 class, E forms a class by itself and these 2 classes. So, there will be 3 irreducible representation. Okay. So, I will have gamma 1, gamma 2 and gamma 3. Now, I have to find out what will be the nature of the characters. So, we have to use in this case rule 1, correct. So, the square of the dimensions of the irreducible representation, if I sum them, I should get the order of the group. So, the order of the group here H is equals to 6, because I have 6 operations, fine. So, this should be 6 now. So, means L1 square plus L2 square plus L3 square equals to 6. Knowing that all the L's are greater than 0 and integer, we can solve this equation only in one possible way, that is 2 of this irreducible representation will be 1 dimensional and the third one will be a 2 dimensional, meaning that it will be 1 square plus 1 square plus 2 square, that will give me 6. So, here let us say gamma 1 is 1 dimensional and gamma 2 is 1 dimensional, then in that case gamma 3 will be 2 dimensional representation, fine. So, here what we can start with is the following. In the previous example, today itself we talked about the presence of a totally symmetric irreducible representation in any given character table, right, and this totally symmetric irreducible representation is always 1 dimensional, correct. So, without worrying about anything, I can fill out at least 1 row corresponding to 1 irreducible representation which is supposed to be 1 dimension. So, let us write down the totally symmetric irreducible representation. Okay. And I know immediately that this corresponds to a type of irreducible representation when if we look at the Mulliken symbol. We can also verify here the rule 2, which is over here, is satisfied, that is summation of the square of the characters for any ith irreducible representation over all the symmetry operations should be equal to the order of the group. So, here if we look at that 1 square plus again 1 square, but I have to remember there are 2 operations here, that is why this 2 is written here. So I have 2 multiplied by 1 square, and similarly here I have 3 into 1 square, correct. So this is equals to 6. So we have verified that, and we can verify for each one of these IRs. Now we have to find out the other numbers here. So I have total there should be 6 more characters that I have to fill in here. Now we have already seen from this clause that this and this should be one dimensional and this should be two dimensional, and dimensionality comes from the character of the identity operation, and they are always positive. So without worrying about anything, I can fill this one. Okay. So then I have to fill other 4. Now let's first worry about gamma 2. Gamma 2 is another one dimensional irreducible representation. So that means all the characters of the representation also will be 1. Okay. In that case, if I have to satisfy the condition 3 here, okay, so any two irreducible representation of the point group will be orthogonal to each other. Okay, that is true for any two irreducible representation. So gamma 1 and gamma 2 should be orthogonal, meaning if say this character is x and this character is y, then 1 into 1, 2 into 1 into x plus 3 into 1 into y should be equal to 0. So therefore I can very easily find what is the value of x and y, because there are total 6 elements in this group, correct. So total sum of the square of these characters here is also 6. That's what I showed here. This is nothing but the chi gamma I of all the r square, right. So I have 1 plus 1 plus 1 plus 1 plus 1. Now here if I have to satisfy the orthogonality, I have to have 3 plus 1s and 3 minus 1. How can I get that? Because here I have 2 characters, so I can put this one as plus 1 and y to be minus 1. Then what I have, 1 plus 1 plus 1 here, then here 3 minus 1s. So if I multiply gamma 1 and gamma 2, I am getting 0. So the clause of orthogonality of two irreducible representation is satisfied in this condition. So now I am left with the third irreducible representation, which is two dimensional. So here also we will use the clause of orthogonality of two irreducible representation, and we have to satisfy that this gamma 3 is orthogonal to any of the irreducible representation of this character table. So in that case, what I can do, suppose I write this one as say again, if I take this one as x and this one as y, while x is the character of the class C3, y is the character for class sigma v. Then I get two sets of equations, right. So when I combine gamma 2 and gamma 3, and I combine gamma 1 and gamma 3. So first take gamma 1 and gamma 3. So what I get 1 into 2 plus 2 into 1 into x plus 3 into this 2 and 3, they are coming from the total number of elements present within a class, correct. So 3 into 1 into y, and this should be 0 due to orthogonality. Similarly, I combine this two, so I get 1 into 2 plus 2 into 1 into x minus 3 into 1 into y equals to 0. Now, if I subtract, say this is my equation 1 and this is my equation 2, and if I subtract 2 from 1, then what do I get? If I take the whole minus of this one, then what I get is, so this 2 get cancelled, okay, and this one also gets cancelled. So, this one I have 6y equals to 0. Okay. So, here I get y equals to 0. So, let me write this here. Now, I can again add this 2 and then I can get the value of x. So, but without doing that also I can easily figure out, because this if I look at rule 2, the sum of this square of this characters of any IR is equals to the order of the group, then 2 square plus 2 into x square plus 3 into 0 should be equals to 6. Okay. So, if I do that, then I should get the value of x, and if I do that, I will easily get x equals to minus 1. Okay. So, also you can verify by adding these two, because here what you will get is, if I add this to equation in the second step, so forget about this minus sign, so you will get 4x equals to 0. Okay. Sorry, 4x equals to minus 4. So, x equals to minus 1, correct. So, here we can put minus 1 here, and thereby I get the total all three irreducible representations. Now, if we come to the naming, so this two are one dimensional, so either A or B. So, if I look at the character corresponding to the principal axis of rotation, then I see both of them are symmetric with respect to C3. Therefore, both of them belong to A category. So, how to differentiate that? So, if I look at the characters corresponding to sigma V, then I see this one is symmetric while this one is antisymmetric. So, this one will be A1 and this one will be A2. So, let us do that, A1 and A2, and two dimensional representations are denoted by the term E. So, this is E, and this point group does not have any inversion symmetry. So, I do not have to worry about adding something like Gerade or Ungerade terms. Okay. So, this is again you can see the totally symmetric IR. That is what we started with. So, this is how you can formulate the character table of any given point group. Okay. And you should try out various different point group and try to formulate their character tables. You should start from a smaller point group, meaning the point groups with number of elements which are smaller, and then go to more rigorous. Now, suppose we are forming directly these character tables of irreducible representation. Now, earlier we showed that you can form any representation which can be reducible. Fine. So, what you can do, you can formulate a matrix representation of that point group, and based on the basis functions that you choose, your matrix representation can be smaller or very large, and many of the cases they may be reducible. So earlier we mentioned that okay, you can reduce the representation, matrix representation, by doing a similarity transformation if you find a suitable matrix to do that, and upon doing the similarity transformation you can block factorize the matrix, and then you can get those blocks which are not further reducible, so they represent your irreducible representation. Now if you really want to do that, sometimes it may be cumbersome because you may have a fairly large matrix representation, and finding that matrix may be quite difficult. So are there any ways to reduce any representation? Okay, so the answer is obviously yes, and that also follows from the consequence of this great orthogonality theorem, and we will see that next. Now one important thing about this reduction of a representation to yield irreducible representation is as follows. So suppose you have a representation having a big matrix and having several elements in it, so you form this square matrix of any order. Now when you do the similarity transformation, what you have, you form this blocks right along the diagonal. So different number of blocks that you can form. Okay. Now when you start with a representation, before block factoring that, you get the trace of the matrix. Fine. So suppose before doing this block factoring, you have a character for a representation. Suppose I call that as a gamma reducible. Okay, because you can reduce it. So this is before block factoring, and after block factoring, when you get these blocks which themselves work behave like a representation, then, and if they are reduced, they are irreducible, that is you cannot find a matrix which can perform similarity transformation on these blocks again and reduce it further. So therefore you get the irreducible representation. Now the good thing is that if you take the characters of these individual blocks which are the irreducible representations and sum them up, and suppose I call it gamma chi of gamma irreducible, okay, and if I sum it over the total number of blocks that I can get, fine. So suppose this is my I and I sum it over I, so I is the number of such blocks, then this and this are equal. That is the nature of this matrix representation. So after reducing, the character doesn't change. So that is a very good thing for us, because that will help us having a way out to reduce any given representation. So suppose I form a representation of the C3b point group. Okay, so for example, I write the representation of C3v again. So C3v okay. So what I can do, I can form the matrix and then I can find the character. So suppose I get the character of my representation as this. Suppose this is my character, and this is reducible. Okay, this is reducible. How do we know this is reducible? Because for any given irreducible representation, this rule 2 should be valid. So chi square, and if I sum it for any given IR, should be order of the group. If it is greater than order of the group, then definitely it is reducible. here you can very easily figure out, okay, 5 square 25, okay, and when you square it all becomes positive, right. So therefore you can easily figure out this is much higher than the order of the group, which is 6. Now how do I reduce it? Okay, I am not dealing with any matrix anymore, I am just directly dealing with the character. Okay, so the way we can do it, we can utilize this property, okay, that is the character of the matrix does not change upon similarity transformation. Therefore, suppose that I am talking about this reducible representation, and the character of the reducible representation is chi of r, okay, for any given operation. Now for any given operation, what I can do is I can reduce this representation, and ultimately what will happen, it will give me those irreducible representations that are possible for C3b, like what we got A1, A2 and E. So depending on what type of basis function I chose at the beginning and the size of the representation, I may have a situation where there will be n1 number of A1, n2 number of A2, n3 number of E irreducible representation will be present if I reduce this large representation. Okay, so I want to know what are the n1, n2 and n3. That's my aim, correct? So I can write any of this character for any given symmetry operations for a reducible representation as the sum of the character of the same symmetry operation belonging to any particular jth irreducible representation. Suppose I am worried about any jth irreducible representation, then I may have some particular number. So suppose I call it Aj. So Aj number of jth IR will appear in my reducible representation when I reduce it, and so there will be several irreducible representations. So J can be 1, 2, 3, whatever. Okay, so I can have this relation, okay, because the character of the matrix does not change on the similarity transformation, correct. So now let us see if we can find a mathematical relation by which I exactly determine the value of this A, okay, that is the coefficient in this equation. So in order to do that, what I can do is I multiply both these sides by chi of r corresponding to an ith irreducible representation, and then I sum it over all the symmetry operations, right. So I can do that same thing here also. So I can sum it over R multiplied by chi of R for ith irreducible representation. So now the order of okay, so what we can see here, suppose I rewrite this one, okay, before even rewriting. So now if I look at this particular part, which is the multiplication of chi j and chi I. Now from relation 3, what we know is that if they are different irreducible representations, then they will yield 0. So this term can survive only when I equals to j. Fine. So if I put j equals to I, then only this term can survive. So therefore, what I can write is okay. So not only that will survive, and that will yield a particular value, which is h over the dimension Li into A I, right. So because when j equals to I, then only I can, this part can survive and can give this value h by Li. Okay, Li is a dimension. For one dimensional, Li equals to 1. This comes from that term in the great orthogonality theorem, that h by root over Li Lj, when I equals to j, then it is Li square. So root over Li square, I am getting this Li. Okay. So now if I look at this Ai, then Ai equals to, if I can write here, Ai equals to Li by h, order of the group, into this, into chi of r, into chi of r for the ith irreducible representation, and summed over all the symmetry operations. So this is a very useful relation for us. This will tell me if I form any representation such as this and try to reduce it. So this will help me doing that job. It will exactly tell me that how many times, suppose if I is equals to A1, then it will tell me that how many times A1 will occur in this representation. In other words, if I reduce this, then A1, a number of times A1 will occur. Okay. Similarly, I can find what is the number of occurrence of A2 or E for this particular point group. Okay. So this relation we should try to remember. Okay. So you can follow this method, you can derive yourself again, and try to remember this one, because this will be used very often. Alright. So now just to illustrate this particular relation, you can apply this one on this particular representation. Okay. So whenever you are given a representation, you have to first see if it is reducible or not. You can check by following the equation 2 whether it is reducible or not. So we have already stated that it is reducible, because the square of the characters, if I add, then it is greater than h. Okay, h is equal to 6 here. So now if I remember what was A1, A1 was all 1. So suppose for example I write A1 here, so A1 was this, correct, totally symmetric IR. Now I would like to find out how many times A1 will occur if I reduce this one. So let's look at that, A1. So Li is 1, so I don't care about that. So it is 1 by h, that means 6. Fine. And then I have to sum this combination. Fine. So I will combine this one and then keep summing, and we have to remember this numbers. So here we missed 3 here. Okay. So I have 5 into 1 plus 2 into 2 into 1 plus 3 into minus 1 into 1. So this gives me 1 upon 6. This is 5 plus 4, 9 minus 3. So equals to 6, meaning 1. So this means that if I reduce this one, I will get A1 only once. I can quickly find out what will be the fate of A2. Okay. So What was A2? A2 was uh, 1 1 minus 1, right. So, now if I try to find out A2, I will utilize this same platform. So, only thing I have to do here, instead of plus 1, I will have minus 1 again, right. So, now what I have 5 plus 4 minus minus plus, so I have plus 3. So, I have 12. So, for A2 I have 12, correct, and therefore, number of times A2 will be present if I reduce this particular representation is 2. So, I got for A2. So, I got say gamma, I can start writing. So, I found A1 which will be occurring once, and A2 will be occurring 2 times. Let us find out what about the E, the representation E, right. So, let me write it here. So, this will be 2, this one was minus 1 and this one was 0. So, similarly, if I do this, so instead of 5 into 1, this will be now 5 into 2, and here it will be 2 into minus 1, and here it will be 3 into minus 1 into 0, all right. So, let us see what is the result. So, I have here it is 10 minus 4 plus 0 means 6. So, I get equals to 1. Okay. So, I get the E representation, E irreducible representation only once. So, what I can write now, this gamma which was reducible equals to A1 plus 2A2 plus E. Okay. So, you can see here that though A1 and A2 are appearing only once, A2 is appearing 2 times. Now, you can also figure out that the characters remain the same. A simple example, if you take the character for identity. So, A1 gives me character 1 for identity, A2 also 1, E is 2. So, A2 is appearing 2. So, 1 plus 2 plus 2 equals to 5. That is what we have. If you check for C3, what you can have, for A1 it is 1, for A2 also it is 1, and for E it was minus 1. So, what you have is 1, you can find that out. So, corresponding to C3, so character for C3 equals to 1 for A1, and for A2 it is again 1, and for E it is minus 1. So, if I add this, that is 1 plus 2 into 1, that is 3, and then E gives me minus 1. So, 3 minus 1 is 2, and if I check here, yes. So, this is verified. So, in this way you can reduce any representation that you can form and find out what are the irreducible representations are present here. So, this is of tremendous importance, because very soon we will try to find out different normal modes that one molecule can exhibit, and we will also try to find out which mode is active toward Raman scattering, which is active toward just infrared spectroscopy, and several other things. So, there what we will need to do, we need to choose a basis set and then form a representation and find out the characters, find out whether it is reducible or not, and then reduce it, and then we have to find this irreducible representation that born out of that reducible representation that we formed, and utilize those irreducible representations that we finally get to do the further analysis, okay, be it normal mode analysis or anything. And so far we have been talking about forming the matrix, but actually without forming any matrix you can still find out the character of the presentation, and ultimately this is the character which you want. Okay, matrix, if you even do not form, if you get the character, then your job is done. So in the following week we will take a very illustrative example, and we will try to show how you can form a presentation without forming the matrix for this one very easily, and then you reduce this thing, and then go to the next level of our analysis. So till then I thank you for your attention, and see you next week.